exponential and logarithmic functions. Exponential and logarithmic functions. And yes, we will start with the exponential function 4.1. Okay, the exponential function looks like this. This is the base. This is the exponent, or power. Why do you think this function is called exponential? Because the variable is the exponent. The variable is the exponent. The base is a number. Now, let's talk about the base for a moment. So the base is given to us most of the time, okay, for the exponential function. But let me give you a few examples. Let's say -1 to the second power, 0 to the third, 4 squared, 1 to the fourth, -3 to, I don't need the last one, I already have an example, but let's say +3 to the second power. Can I raise -1 to the second power? What do I get? Perfect. Can I raise 0 to the third power? What do I get? Perfect. Can I raise 4 to the second power? 16. Can I raise 1 to the fourth power? 1. Can I raise 3 to the second power? No. Perfect. However, this, and this is not allowed when it comes to exponential functions. For only one reason. We can determine those numbers. There is no problem. But there is one reason why we cannot accept a negative base, a 0 base, or 1 base. Base of 1, 0, or a negative number, any negative number, because of this function, log. Log will not exist if we allow these 3 bases in the exponential function. And log will be the inverse function of the exponential. So what can a be? There are 2 possibilities. For a to be between 0 and 1, a tiny number, not 0, not 1, not negative, or a number greater than 1. These are the 2 possibilities. So this complicates things a little bit. Why? Because the exponential function will look in a certain way if the base is small, between 0 and 1, in a different way if the base is greater than 1. So there are basically 2 different shapes, 2 different looks for the exponential function because of that. So an example of this will be f of x equals 1/2 to the x. An example from this will be f of x equals 2 to the x power. They will look totally differently. Why? Because the base is different. Okay, so let's start with the first one. Let's look at f of x equals 1/2 raised to the x power. Like before, we will start with the table. We will identify the domain and then graph it. We want to understand the properties. We want to look at it. We want to see how it looks and what it does for future applications. Okay, so what do you think about the domain of this function? Correct. The power has no problems whatsoever. I can have a negative power, I can have 0, I can have 1, I can have positive. The power is not a problem. So this I would say friendly. So-called friendly function. Why? Defined everywhere. I don't have to worry about it. I don't have to state restrictions, nothing.
So if it had restrictions, what would it look like?
But it doesn't. It doesn't have any restrictions. For example, here's a function with restrictions. This one, the square root of x. Another function with restrictions is a rational function. It has vertical asymptotes. It's not defined everywhere. But this one is like polynomial functions. Polynomials have no restrictions. This one doesn't look like that, but it has no restrictions. It's defined everywhere. Friendly function. Good. So let's pick some numbers. Just a few. -2, -1, 0, 1, and 2. And let's see what we get. So let's replace x by -2. F of -2. Let's replace x by -2 here. Let me refresh your memory on negative powers, in case you forgot. So a to -n is 1 over a to the nth power. If we are having like this, 1/2 raised to -2, we flip the fraction and this becomes 2 squared. Okay, let's cross it out because I'm not sure I convinced everyone. So it's 1 over 1/2 to the second power, which is 1 over 1 square, 1/2 times 1/2, which is 4. That's how we got this 2 squared. Okay, so this is 4. Can anyone plug in -1 and tell us what is the result? Very good, awesome. Can anyone plug in 0? Let me refresh your memory on this. Any number raised to 0 is 1 except 0 raised to 0. 0 raised to 0 is not 1. Okay, so I plug in 0, 1/2 raised to 0. What is the answer? 1. Let's plug in 1. What do we get? Very good. Let's plug in 2. What do we get? We just 1 over 4. Perfect. Now, this is not the way we determine the end behavior for the other functions, but it works here. Totally differently, right? I'm going this way. 1 over 4, 1 over 2, 1, 2, 4, 8, 16, 32, 64, 128. Where am I going? Perfect. I am going towards infinity. Let's go the other way now. I have 1 pie, whatever you like, apple pie. I eat it by myself. Then I eat it with 2 people, then with 4 people, then with 8 people, then with 16, then with 32, then with 64, then with 10 million. How much will I get from it if I want to do nothing? No. Yeah. You can't. I cannot give something I don't have.
Infinitely getting close to 0, but you're probably never actually going to hit 0.
Right.
So it's almost like an asymptote, but not exactly.
It is.
Oh, is it?
Y equals 0, horizontal asymptote at infinity only. As you see, there is no 0 here. So that's not a horizontal asymptote. Only here. We're ready to graph this function. Let's see how it looks. So can anyone dictate the first ordered pair? Very good. -2, 4 it is. Next one. Very good. Next one. And from now on, it becomes difficult for me to plot it. This is the function, 1/2 to the x power. It has tons of properties. So exponential function with base 0, between 0 and 1. Properties. 1, domain. Thank you. Range. Very good, awesome. Thank you. X-intercepts. Of course, thank you. 4. Y-intercept. Always. For a pure exponential function, the y-intercept will always be 0, 1. If it has transformations, it's a different story. We're going to look at transformations in a minute. 5. Increasing or decreasing on all its domain? Of course. It's coming from positive infinity and approaches 0. Asymptotes.
Y equals 0.
Very good. Only at infinity. 7. Is it 1-to-1? 8. Does it have F inverse? Of course, because it's 1-to-1. Let's graph it. Can I graph F inverse? I know nothing about it. Can I graph it? Of course. Remember, I did not see this on your test, except one. I did not see this function or this line, y equals x. When I graph the function and its inverse on the same coordinate system, I must graph y equals x. Why? Because this point belongs to both functions. If the function crosses y equals x, the inverse will cross at the same point. Good, so now please give me a couple of ordered pairs that will help me graph the inverse function. 4, -2, awesome. Perfect. Then, very good. Careful.
1, 0.
Perfect. That's all I need, and I have this point already. So this is F inverse. For now, we don't know what it is. But would you clearly identify and say, if the exponential function has a base less than 1, it's decreasing, its inverse function will also be decreasing? Would you say that? Yes. So in both events, for both functions, the base less than 1 makes them decreasing on all their domain. Okay. Now let's look at this function for one moment. Can anyone give us a domain of this function, the inverse one? Not the function, we know the exponential is defined everywhere, but can anyone give us the domain of the inverse?
0.
Right. It's not a friendly function. In that respect, it's not defined everywhere. I have to think of the domain all the time. Like the rational function, like the root with an even index. So this function will join that other group of two functions, rational and radical. It's not defined everywhere. It also has what? A vertical asymptote. So keep that in mind. This is a friendly function. This one is not. This is the function we just graphed, but we don't know that yet. In a minute, we will. A few minutes. Okay, so now let's graph the other shape. What other shape? Well, there is a second shape for the exponential function, with a base greater than 1. Again, let's determine the domain and get the table going. Can anyone give us the domain of this exponential function? No matter what the base is, the exponential function is always friendly. I'm going to use the same numbers from before, -2, -1, 0, 1, and 2, only because it has nothing to do with the base, only because are simple numbers to work with. So then